Good morning, everyone. Okay, so I'm here to make a presentation on the in-situ measurement of air quality. My name is Dr. Rose Alani. I lead the Air Quality Monitoring Research Group of the University of Lagos, Nigeria. So, next slide. So, when we talk of in-situ air quality measurements, it's not just real time. We have active sampling towards obtaining data, and we have passive sampling, and then we have the real time. So what I'm showing you here, it's a bit of the passive active monitoring of air quality in Lagos. That other one that is a bit dark, it's not showing well, but it's when I was climbing up to the 3rd floor to mount the active sampler. And you can see there, here we're using cyclone, and we have a pump. So that pump is connected to a flow meter that records, I think I should use this. It's connected to a flow meter that records the flow rate. And then it's also connected to a timer because we want to collect the sample for 24 hours. And so sometimes, because this depends on electricity, the power might go off, so it might not collect for the complete 24 hours. And so the timer will tell us when the light went off and when it came back. So we'll be able to record and know the exact number of hours. And so I wish I have a pointer. So no, please don't. Just go back. So from the second picture you see there, you can see a cord linking up. So it links up to the 3rd there, where you have the okay. So this is the flow meter. Can you bring it down a bit? No, up. So here is that flow meter. Bring it down. This is a pump. So this is the flow meter. It's linking up here. And then bring it down. So that's where it comes out of the window, and we clamped it here. Here is a cyclone, and then the filter is here that we used. We don't put the filter directly. We put in a filter holder and then open the cyclone and fix it. Yeah, open it and fix it. And then we monitor the flow rate and also the timing. Like I said before, I don't want to go to the size of the PM 2.5 because Dan has already done justice to that. And if you want to get more information about this 5 million and so on, you can see it, this link. Next slide. So just showing a little bit of the result we got, because this paper is not yet published. And so this is what we got, concentrations and the days. We carried this one out in the month of May 2023, collecting the filter, collecting the sample on Teflon filter, and then analyzing it using energy dispersive X-ray fluorescence. So we got this. And then we had to see what is contributing to what. So we saw the sulfur-rich formation here, sulfur-rich PMs. See the different percentages here and what is responsible for that. Sulfur aerosols emitted from fuel combustion. Of course, we know of the vehicular source of air pollution, PMs. So the chlorine rich from marine aerosols, you also know we have the lagoon in Lagos there. And then the biomass, a lot of burning. We have the chlorine, potassium, and so on. Zinc, lead rich, get them from car exhaust, industrial emissions, cement sources, and so on. So actually, the contribution here for the PM 2.5 is not complete because the X-ray EEDXRF is limited to some of those pollutants that it can read, not reading carbon, black carbon and organics and so on, which is also part of the PMs there. So this is just a way of just suggesting a bit what it is. Please, the next slide. So we also are involved in the GAPS, which is a global passive air sampling, which involves 19 cities globally. So you can see here, and you see us here, the Air Quality Monitoring Research Group, and this is my group collecting the samples. You can see the polyurethane foam here, PUF. This is clean before it is mounted, and then see how it is after 3 months, collect quarterly. And then, you know, for this, it's not what you get the result immediately. You have to go use some instruments and analyze. This one, we did it in Guangzhou Institute of Geochemistry, I and my PhD student at that time, analyzing the organics in that lab. So next slide. So we got some results here. Actually, the pollutants, organics, we're looking for the flame retardants, OPEs, and so on. All these were what we're looking at. And we found out that New York and London stood out. New York, #1, most polluted, and then London, the next one, ranging from 3.5 to 30 times higher than the total flame retardant concentration when you compare to other cities. So, and then, so can we see the other one? Next slide. So this is how it looks like globally, the 19 locations for organics. So we see here New York for this particular one, for the OPEs. New York is #1 here. So if you could check here, and then next one, okay, Toronto is #1 for this. And then, so you can check it there. Okay, thank you. Thank you. So here, New York is #1 there. And then this is London, #2 from what I showed you. This is us here in Nigeria, in Lagos. We're a bit down in this one. But let's go to the next one and see the location where we are. So for this one, this set of pollutants, the dichlorines and dichlorines, Nigeria were #1 and others follow. So can we move it? Next slide. So before you move to the next slide, the publication is here. If you want to see details, you can see here, check here. I think after this, we can give you the slides. So here also just comparing. And so why did I start with active and passive sampling? I started with this because we want to see what is the solution to air quality problem globally and especially in Africa. So these passive and active, are they the solution? What are the setbacks? And what do we get? So the setbacks you can see is time consuming, even though sometimes, like for the passive sampling, the sampler is quite cheap. The PUF and that sampling jacket is quite cheap, but you cannot and get the result immediately. It took us to travel to China to be able to analyze. It also takes 3 months for us to sample and take for analysis. And it also takes expensive equipment, instruments, solvents, all sorts of things to prepare the extract and then analyze. So that's the implication of this. Also for the active, it also takes time, even though within 24 hours you can collect your sample, but you need to go and use an instrument to carry out analysis and so on. So this one we analyze with GCMS-MS. Next slide. So we see generally that research grade pollution data globally is very, it's scanty. So you can see here, less than 1% is in most of the places here, So it's really very scanty and we have a lot of work to do. Next slide. So are low-cost sensors the answer? Because we have seen problems. Are low-cost sensors the answer? So let's see what we get there. Reference monitors can be very expensive. From 25, I'm short, I don't even think we can get it 25,000 again, because BAM, like today, is like 39,000. So low cost sensors are quite cheap. And the low cost sensors can also be used for policies and so on. And then dense urban network of low cost air pollution monitors have been used for some actions improving air quality in different places. I have used these ones. I've used Air Quality Egg, which I will show you some work we've done with this. Air Quality Egg, and then Airco, and then this is RAMP, and then Purple Air, and an AQ Mesh. Next slide. So just showing that all these ones are they're quite cheap, and they contain, all of them, they contain plant or PM 2.5. That means that these sensors use laser light scattering. That's the principle it uses to measure the value of dust that is collected, in this case, PM 2.5. Next slide. So there are 2 classes of PM sensors. We have the truncated nephelometers, and we have the optical particle counters. So the first one, it measures the scattering particles as ensemble, that is not focusing on a particular particle. It's capturing a group of particles and the scattering for a group of particles. And also it has another limitation of not being able to measure beyond 1 micron. So between 200 nanometer to 1 micrometer. And we have some lists here of some of those low-cost sensors that fall within that class. We have the optical particle counters. These ones measure the scattering of individual particles. So, and it also provides information for a larger range from 350 nanometers to 40 microns. And so this particular one will cover our area of interest, PM 2.5 and PM 10, and so on.